Today we will be looking at section 10.8. Section 10.8 is all about power theorems. Power theorems deal with segments and finding the length of a segment given a circle. So the first power theorem is called a chord-chord power theorem. It states if two chords of a circle intersect inside the circle, then the product of the measures of the segments of one chord is equal to the product of the measures of the segments of another chord. So anytime you have two chords intersecting, like in this picture down here, we've got the chord AC and BD, and they're intersecting at point E. Notice how the formula states that, okay, the chord AC is created then by AE and EC. So multiply those two parts together, and that equals the second chord BD, which is broken up into BE and ED being multiplied together as well. So here we have an example that states that we have the segments of PW, where WP is 2. We're told that PZ is 8. Notice that those two little pieces form one of the chords WZ. The other piece of information we're giving is that XP is 4. Our goal is to figure out what the length of PY is. I'm going to call that X. But notice that our XP and PY form another chord. So using that chord-chord power theorem, I can take 2 times 8, multiply them together like this, and set that equal to 4 times X. So 2 times 8 is 16. 4 times X is still 4X. To solve for X, I'm going to divide both sides by 4. X turns out to be 4. Now, because X is representing PY, and that's what I'm trying to find, this is my answer. Taking a look at the next example, notice how we have AC is a chord, BD is a chord, they're intersecting at E, so we're using this chord-chord power theorem in order to find the length of the segment ED. So what we're given is that AE is 3, we are given that EC is 12, and so because those two pieces form one of the chords, I get to multiply them together. On the other end, I know that BE is 9. Once again, ED is what I want to find, so since I don't know what that is, I'm going to call it X. Those two pieces form the second chord, so I get to then multiply those pieces together. Well, 3 times 12 is 36. 9 times X is still 9X. To solve for X, I'm going to divide both sides by 9. X equals 4. Once again, X is representing ED, and that's what I'm trying to find. So once again, our answer is 4. I do want to just point out that your answer will not always be 4. It just happened to be that these two examples were. But that's how the chord-chord power theorem works. Our second power theorem is called the tangent-secant power theorem. It states if a tangent segment and a secant segment are drawn from an external point to a circle, then the square of the measure of the tangent segment is equal to the product of the measures of the entire secant segment and its external part. So remember, a tangent is a segment that only touches the circle one time. In the diagram here, the segment DC is a tangent segment because it only touches the circle at point D, and notice that C is outside of the circle. Our secant segments, secants touch the circle at 2 spots. Notice that AC is that secant because it touches at A and B, and once again, it goes outside the circle at C. So notice that both of those segments are meeting externally at point C. So once again, if we square the tangent segments, that equals the whole secant times the external part. Now remember, external means outside of the circle. Another way to help us kind of remember this power theorem is to think about the phrase we. I know that's a little bit funny, but when I'm talking about we, I mean that W stands for the whole part and E stands for the external part. And it works for this tangent-secant power theorem. Notice that DC is the whole entire tangent segment, but notice that it's also everything that's outside of the circle. So the whole times the external is why that tangent is actually being squared, because you multiply it by itself. Then the whole entire secant AC is multiplied by the external part BC, which is outside of the circle. So anytime you want to think about a tangent secant power theorem, you can just think about that phrase we. So looking at this example, notice that I'm giving us that ML is 6. That happens to be the tangent in this problem. KL is 4. Notice that that is an external part because that segment is outside of the circle. What we're trying to find is JL. Well, JL, as we can see, is the whole entire secant. Since I don't know what that is, I'm going to call that X. So once again, using that tangent-secant power theorem or thinking about the phrase we, if I start with the tangent, 6 is the whole entire tangent, but it's also the external part. So 6 times 6, or 6 squared, will be the first half of this equation. Then I look at the secant. The secant is the whole entire thing is x, and its external part is 4. So that's why this part of the equation is x times 4. So now solving for x, 6 squared is 36. X times 4 is 4x. To get x by itself, I'm going to divide by 4. I get x to be 9. Once again, x is representing the segment of JL. That's what I'm trying to find. So I am done. If I look at this next example, notice that AC, this whole piece, which happens to be my secant, is given to us as a length of 12. AB, which is the chord that's inside of the circle, is 5. Now, once again, if you're thinking about the phrase we, 5 is not the whole piece, and it's also not the external part. So 5 is not actually going to be the number that we want to use in our equation. But notice that because the whole entire secant is 12 and 5 is a part of that secant, I can definitely calculate this external part by subtracting those two numbers. So the external part that I actually need is a length of 7. Notice that what we're trying to find is the tangent DC. I'm going to call that x. So once again, if we think about we or the tangent-secant power theorem, we want to take the tangent and square it, or once again, the whole piece times the external is x times x. Then moving on to the secant, the whole piece was 12. The external part is 7, and so 12 times 7 finishes up that equation. X times x is x squared. 12 times 7 is 84. In order to get x by itself, I want to get rid of the squared term, so I have to take the square root of both sides. That gets me x by itself. When you take a square root in an equation, you normally have two answers, both a positive and a negative. However, x is representing the length of a segment. There's no such thing as a negative length, so we only want the positive value. Square root of 84 is not a perfect square. However, we can break it up and get a perfect square. Notice that this is really 4 times 21. 4 is a perfect square. The square root of 4 is 2. 21, while it can be broken up into 7 and 3, you are not going to be able to get any more perfect squares out of it. So 21 is going to stay underneath the square root. So x equals 2 root 21. That is what I want my answer then to be, because that's representing DC. I just want to once again point out that not every number that we get in our original problem is actually going to be the number that we use in our equation. So just be very, very careful of that. Our last power theorem is the secant-secant power theorem. It states if two secant segments are drawn from an external point to a circle, then the product of the measures of one secant segment and its external part is equal to the product of the measures of the other secant segment and its external part. Okay, so once again, you can think about the phrase we. Whole times external equals whole times external. So if we're looking at this first example, notice we are given BC to be 6, AB to be 9, CD to be 5. We want to find CE. So I'm going to call that X. So once again, if I'm thinking about whole times external and I start with the secant AC, I'm not given what the number for the whole entire secant is. However, because I'm given what each of those pieces are, together they form the whole piece. So we have to add those numbers together to find out that 15 is going to represent the whole piece. Our external part would be 6. So we'll have 15 times 6. Notice that x is representing the whole entire secant on the other side. 5 is its external part. So notice that now that we have our equation, we can start solving for x. We've got 90 equaling 5x. I'm going to divide both sides by 5. And so we get an answer of x to be 18. X is representing CE. CE is what I'm trying to find. So 18 is my final answer. So once again, 9 and 6 were not both the numbers that we were using with our secant. We had to add them together in order to use the true number in this equation. Our final example here, we're told that AC, the whole entire secant, is 10. I know that DE is 4. I know that CD is 5. We want to find AB. Notice that AB is representing the chord that's inside the circle, but if we think about the phrase we, I want the external part. So I'm actually going to make X represent BC instead. Notice that on the other end, I'm going to have to find the whole piece by adding 5 and 4 together. So that would turn out to be 9. So my setup for this one would be 10 times X, and that's going to equal 9 times 5. So this ends up being 10x equals 45. I'll divide by 10, and I'll get x to be 4.5. But remember, x is representing BC. My goal is to find AB. So 4.5 is not my final answer. To get that internal part, that chord, I'm taking the whole secant, which was 10, and I have to subtract the external part from it. So when we subtract that, we'll get our true answer, which is 5.5. So just be careful what you represent x as and make sure that that is truly then what your final answer is. In this case, my x was not my final answer. So these are our 3 power theorems.